Good afternoon, everybody, and welcome to the final presentation of the workshop on innovative systems. In these few slides, it will be presented an overview on the workshop course and on the organization of the event. Let's start with the history of this workshop. In the first edition, we focused on the architectural and physical design of logic and memory devices. Then we moved to the neural networks and arithmetic logical units. In this final edition, we focused again on the arithmetic logical units, but a particular attention is given to the architectural and the emerging technology exploration and characterization. The motivations behind this workshop are linked to the assumption that the digital design is becoming increasingly important, requiring advanced skills. These skills can be hard skills, so for instance, the ability to do a research, to approach real-world problems, or simply to learn something about the digital design flow, but also the soft skills, so the ability to cooperate, to explore, and also to solve problems. The roadmap starts with the definition of the specifications, so in our case is to design an ALU. Then we move directly to the study phase, taking material from the literature, but also from the previous workshop edition. Then we move directly to the architectural phase, in which the students define the common design guidelines, implements a first version of the ALU, the so-called ugly duckling implementation, so without any optimization, and then moving directly to applying some of these optimizations in terms of low power, high speed, and mixed speed power. The final phase is the technological one, in which the students had the possibility to design their blocks at the transistor level by using Cadence Virtuoso. This design is performed with emerging technologies such as tunnel FET for a low power optimization, gate-all-around FET for a high-speed implementation, and FinFET for mixed speed and power. The organization of this workshop, we have 12 students divided in 3 groups and 1 year time to develop their version of the ALU. During this time, the students acquired new abilities such as design skills, team building, cooperation, and creativity. The courses involved starts from the first year of the master degree, in particular with the course of Sistemi, elettronici, basso consumo, in which low power techniques and advanced digital design flow are explored, and a course of the second year of the master degree, integrated system technology, in which a deep study of CMOS and emerging technology fabrication is performed. Regarding the groups, we have the low power group with Diego Bert, Lorenzo De Carlo Chimienti, Lorenzo Lagostina, and Andrea Sellini. Then we have a mixed power delay group with Vlad Pancila, Ilaria Bosco, Paolo Giordano, and Michelangelo Miceli. Finally, the high speed group with Francesco Barbaro, Pier Francesco Boccardi, Alessandra Dolmeta, and Sara Zamiglia. So now it's time for the group, and I leave the stage to the low power group. Thank you for your attention.
Okay, probably before starting with the first group, if the Professor Maurizio Zamboni and Gianluca Piccinini would like to say a few words concerning the organization and the experience of the workshop, they are very welcome.
Okay, can you hear me?
Yes, thank you.
Okay, thank you. If you want, I can start. I don't know if my colleague, Professor Maurizio Zamboni, is connected now, but thank you to Andrea for the very clear overview of the workshop and on the methods that students use and you use during this experience. So I would like also to thank all the persons that with their effort made possible this work. So in particular, I want to thank Yuri Ardesi, Andrea Coluccio, Chiara Spano, Fabrizio Mo, and Fabrizio Ottati. Thank you a lot again for your very high level, high effort work during this long year of workshop. So I want to to say a few things because I prefer to hear the presentation and I want to limit the time of my speech. So what I want just to underline is the added value of this workshop can be, from my point of view, identified mainly in the experience of the use of new technology and the impact of new technology on systems. So many times for students, advanced technology seems quite far from their possible experience. And so this is a problem from my point of view, and is a problem in general, because I think that for an electronic engineer, it's very important to know which are the main consequences of the technology choices on system. And what this workshop did is exactly that. So after this workshop, probably all the students involved in this work have a higher sensitivity, or high sensitivity, I hope, on the consequence of the technological choice on the systems. And for this reason, I think this workshop is very important for you and for the student that in the next year will decide to continue this type of experience. So thank you again, and now I can hear what you did with high attention. Thank you.
Okay, thank you, Professor Piccinini. Probably now we can leave the stage to the first group, that is the low power group. So I ask to the students that are involved to switch on their cameras, and we can start with the presentation. And at the end of each presentation, there will be a question and answering time, just for a few questions. So we will try to handle the time. And at the end, it is possible to ask additional questions if desired. So thank you.
Good afternoon to everyone. We are the Low Power Group, and we would like to show you the work that we have done during this last year. We wanted to achieve different goals for our project. In particular, to expand an ALU that we inherited from the previous group of the last year, by exploring different low power techniques with the final aim to deliver to the next year students a completely reusable project. And for what regards the technology aspect, the technological aspect, to assess the impact of the TFET technology on the power consumption, and also to start the creation of a complete TFET cell library, also providing materials for the creation of future technological libraries independently on the target technology. For what concerns the first architectural part, we started our journey studying the previously done work in order to become aware of the already existing blocks in the inherited ALU. We studied the reports and understood how our colleagues operated, and then we proceeded by studying in literature other possible blocks to implement in the final design. Here you can have an idea of the different blocks which are present in the final version of the ALU, both the integer one and the floating point unit. For what concerns the floating point blocks, it is important to remark that the IEEE 754 standard has been adopted in order to have a work which is compatible with the one of the previous year. But before starting to implement the new blocks, we set up a meeting with the other groups in order to discuss about the standardization of the interfaces in order to make our operators fully compatible with the ALUs designed by the other groups. First, we decided a common nomenclature for signals, consisting in the format that you can read here, such as entity, direction of the signal, and then finally the signal name. We also decided to move the opcode decoders inside the ALU and the FPU entities instead of having just one outside of them. And finally, we decided to have exactly the same flags for the blocks which are in common among the different groups in order to guarantee compatibility. And this last point implies that in some cases we also had to completely refactor the code of the last year, yet functioning, but in some cases some flags were missing. And to test the operators with the modification that we brought, we improved the workflow that was developed by our colleagues last year, exploiting Python scripts for input generation and for results checking, along with Mentor Castasim for simulation and the synthesis step exploiting Synopsys design compiler. The power estimation was performed after an automatic back annotation process that let us obtain more realistic values. And finally, of course, all these steps were not performed manually. Indeed, the work was simplified a lot by the use of shell scripts. It was made automatic, let's say.
I think we have a problem with our colleague that has a connection problem. So
okay, so now probably someone else can proceed with the presentation. I'm sorry for this inconvenience. Moreover, it was also told us that from home it is not possible to see the webcams. We are sorry, but we don't know how this is, why there is this problem today. We are seeing correctly everything, and we are also recording in the correct manner everything. So at the end of the final recording, there will be the possibility to see also the students.
Can you bring me back to more?
Okay, Diego,
can you hear me?
If now the problem is fixed, probably you can proceed with the presentation. So we will leave you the floor.
He's now moderator.
Okay.
Can you hear me?
Yes.
Yes, you're welcome.
Sorry, I can't. I have connection problem at the moment. Before it doesn't happen. Sorry. Oh.
Okay, it was told us that from home it is possible to see the students. So the problem If someone from home is not able to see the webcams, it's simply because he or she has a connection problem. So if you don't have connection problems, the cameras are possible to be seen. So this is not a problem. Unfortunately, we have again lost Diego, if I well understood, because probably he still has connection problems. Is it right? Probably Lorenzo, Andrea, you can confirm that he has connection problems, right?
Yes, I can proceed if
Yes.
there are some problems.
I think this is the best thing to do. And if at the end Diego is able to solve his connection problems, he can add something at the end of the presentation. So I will ask you now to proceed with the presentation. Thank you.
Okay, so now we proceed with the design. So we are presenting here a case of study, the integer square root that we designed in the first part of our workshop. We studied two microarchitecture of the integer square root, the restoring algorithm and the non-restoring algorithm. The low power technique that we applied were pipelining and clock gating. So we were able to save power by applying this technique. And we also then applied this technique to the integer comparator that was also designed with the precomputation technique that also was able to save also power with this technique. So the main step that we did after the design were the synthesis.
Can you hear me? Can
Yes.
I continue? Sorry for the connection. Okay. Sorry, guys. I can't open my video because I some connection problem. Okay. As Andrea was probably saying, we short insight into the two blocks. We can move into the entire synthesis of our ALU. Can you hear me?
Yes, thank you. It's a pleasure to have you again with us. So you can proceed with the presentation. Thank you.
Can you hear me?
Okay, evidently the system is very unstable, Diego, unfortunately. So probably it is better at this point if Andrea, Lorenzo, or someone else would like to proceed to the presentation in place of view. I'm very sorry for this inconvenience. Unfortunately, there is this technical problem. So probably who wants to proceed? Andrea, I see that you have already switched on.
Yeah, I can proceed.
Thank you. Yes, please.
Yes,
please,
so
thank you.
I can proceed with the synthesis and placer route of our design. So we basically, as Lorenzo said, we use a design compiler by Synopsys, and we exploited some feature by this tool. Basically, we developed two versions of our synthesis: the basic version with the command compile, and the OPT version with the compile ultra command. So what we want to highlight here is that compile ultra is a powerful tool in our work, since we were able to save power and also timing and area, because this command were putting more effort in the mapping and optimization of the gate level netlist. So then we move to the placer route part with the Innovus cadence tool, where we faced with a problem in the beginning of the all-time violation, since we, as reported here, we find out that some paths were violating the all-time. So we try to adjust this problem by moving the input-output pins of our ALU in different positions by modifying the physical design. in the end, this is our final layout of our ELU, and the final results are that we can also save power with the top level hierarchy of our design with the compile ultra strategy. And the power contribution are reported here, and the majority of power is made of leakage, and so we will see later why TFET is good for improving this parameter. And we also performed some analysis on the switching activity, since we can perform the integer operation or floating point operations and seeing if which instruction, which opcodes are consuming more power. We can see that floating point operation, of course, consume more power than integer operation. So now we can proceed to the second chapter of our presentation regarding technological study. So the goal of the second part was focusing on the technological mapping of our RTL design that we implemented in the first part, and we were the goal was to study a new beyond CMOS technology, the TFET, and try to compare it with the 45 nanometer CMOS NAND gate open cell library that was already provided. And then we moved on the development of our TFET library by using Cadence Liberate, and we tried to synthesize the integer square root module and try to verify and measure the power consumption. So as I said, we started by analyzing the 45 nanometer CMOS library, and we developed a simple test bench in the Virtuoso Cadence environment. And so with this, we measure the static power and dynamic power, and moreover, we measure the I-on, I-off, and their ratio. And because this ratio is one of the main motivation why we would like to move to the beyond CMOS technology, because we would like to improve the ratio. And so we moved on to the TFET model that is provided by the University of Notre Dame. It is a simple analytical model implemented in Verilog A, and it is based on the aluminum gallium antimonite heterostructure. And the electrical circuit is reported in this slide. You can see that the circuit is very simple and ideal. And moreover, by looking at the model parameters, we find out that the resistance were set to 0. So the final result was the circuit very simple and ideal for our analysis. So by looking at the analysis, we plotted the trans characteristic of the NTFET, and we measure the I-on, I-off, and the ratio. And we can see that with respect to the CMOS 45 nanometer library, the ratio is improved by 30 times, but the trade-off is that the I-on is decreased by 70%. So we expect less performances, but the main contribution is the cutoff of the leakages current that is decreased a lot. But some problems are highlighted here of the TFET, since we can see that on the VGS plane, we have a more zone of operation of the TFET. The KNZ zone of operation is the one that we have also in the CMOS traditional library, when VGS and VDS are greater than 0. But we have current also in the NDR region, where when the VDS is less than 0, and also in the ambipolar region when the VGS is less than 0. So we can see by analyzing 2 cases of study some limits of the TFET technology. For example, we can see here the 2 transistor inverter composed of a pull-up transistor and pull-down transistor, and we reported here the voltage transfer curve, and we can say that by looking at the static analysis, the inverter has a low noise margin, and it can be a problem in static RAM application due to high leakages currents. So we proposed a 6 transistor inverter that shows a more ideal voltage transfer curve, but with the drawback of a bigger area and higher delays. The last case of study is the NAND2 cell, where we can see that the output of the cell rises when one of the inputs rises, and this was a problem in the circuit design, and this was due to the low output capacitance. So we tried to make a trade-off between the output capacitance and the delays by modifying the channel width. The final choice was to choose a channel width of 300 nanometer that we exploited in the next design part of the library.
Please, Lorenzo, we cannot hear you, so probably you should switch on your mic.
Yeah, sorry, I forgot the microphone. Okay. Coming to the last part of our presentation, I will explain the two paths we explored in order to observe the effects of the TIFET technology on a digital design. The first approach revolves around the manual implementation of the restoring design of the square root unit on Cadence Virtuoso. In order to quickly verify the correctness of our design, we exploited an analog mixed signal simulation, which allowed us to reuse the same Python scripts of the low-power design for input generation and results checking. We then proceeded to the manual implementation of the design using 45 nanometer CMOS technology. Once we verified this design, we replied the implementation step with the TIFET technology. However, the simulation reported errors in the results. These are imputable to either errors in the topology or in the interfacing between the testing units and the analog netlist. The second approach we explored is the development of our own TIFET library and the synthesis using Synopsys. We used the NAND 45 library of the North Carolina State University as a reference model, and then we used the standard with which highlighted Andrea before as base width for all of our cells. Then we realized all of the cells implemented in the reference library we use for a total of 126 TIFET-based logic cells. We then passed the Spectre netlist of our cells and the Verilog A models of the P and N TIFET transistor to Cadence Liberate, from which we obtain our Liberty file. It's important to highlight the importance of the TCL scripts during the characterization process, of which we produced a brief guide for future developers. We then converted the TIFET library in a database format, and by using it inside of Synopsys, we managed to resynthesize all of the design of the square root unit. From these, we managed to extract timing and power analysis. However, due to all the time errors inside of some sequential cells, we could not execute the functional verification and back annotation procedures. Looking at the obtained results, we can observe an improvement of the critical path and also an increase in the dynamic power in the optimized designs. These unexpected results are explained by the lack of the layout of the cell and by the ideality of the model we exploited. We can also observe a significant reduction in the short circuit power, but the most interesting and exciting results comes from the leakage power. In fact, it decreased of 3 orders of magnitude, allowing us to demonstrate the potential advantages of the TIFET technology on a wider design. That's all from the low power group. Thank you very much for your attention, and now we are available to answer to any of your questions.
Okay, thank you to the low power group. Now it's question and answering time. So if anyone from home has a question, can type the intention to make a question in the chat, and then we will give you the word. So besides the technical issues, this is what happens when you make live streaming. It's usual. The presentation got at the end. So we are at the end of the first presentation. At the moment, I still don't see questions from home, but I see a question here. Yes. From Politecnico, so please.
Okay, actually, I have a question, and I'd like to ask if you can tell me something more about the standardization. So what's the purpose of the standardization that you applied in your design?
I think I can answer that. I try to move back on the slide. But anyway, the main reason of put so much effort into standardizing our interfaces is because when someone will inherit our work, they should be free to use which blocks they want from each of the different ALUs. Let's say, for example, if they want to design to use a final ALU with some blocks for from our floating point unit, for example. Square root low power to save power because it is a critical, very critical operation. For example, they could use our block, and instead, if they need, for example, a faster adder or subtractor, they can use one of the high-speed group, and in this way, this can be possible. I don't know if my colleagues want to add something.
Yes, I think you explained it quite well. Basically, the final purpose was to make it so easy to change to reuse a block of a certain root or one from another. The PhDs use this image of making it so easy. It's like when you use different Lego bricks from different sets, they all just can be put one beside the others without any issue.
Okay, thank you.
Thank you.
We have another question here.
No, it was the same question, basically.
At the end, it was the same question. So you have already, okay, thank you. So you have already answered. Probably since we are a bit late, we can proceed with the second presentation. And at the end of all the three presentations, if there are already questions concerning the presentation of this group, you may write it in the chat. So now I ask to the second group to switch on the cameras and to prepare for the presentation. The target of the second group was the best optimization between delay and power dissipation. Okay.
Hi, everyone. Hello. Can you, okay, perfect. I will just start from the beginning and saying good afternoon to everyone. I'm Paolo Giordano, and I'm the first presenter of the team that implemented an high-speed and low-power ALU. We can start with a brief overview of the work done so far for the design part. So first, we studied scientific paper to analyze the new architecture to add to the already existing ALU from the last year workshop. Then we standardized the ALU interface, also adding a division between integer component and floating point components. And finally, we developed new arithmetic operators. Since we are interested in a high-speed and low-power trade-off, our figure of merit are the power delay and the power delay area product. Talking about the design and verification flow, the first step is the functional design. We describe our component in VHDL using the ModelSim tools, and still with ModelSim we perform simulation. The verification instead is made with some Python scripts that we take from the last year works, and to also automatize the process. In particular, First, we generate some input sequence that are used to simulate our component, but also a reference model made in Python. Then the results of the two simulations are compared to ensure the correctness of the component with respect to the reference model. We proceed with the synthesis steps using Synopsys Design Compiler, while Cadence in Novus is used to carry out the final place and route step. Proceed with the design of the arithmetic blocks. We start talking about the integer ALU and in particular about the sign comparator. The sign comparator is made by a parallel prefix adder, which has a tree structure. The structure promises to achieve a logarithmic delay, and it performs the sum between A and the choose complement of B. Looking at the final carry out, we can understand if A is greater, lower, or equal to B. About optimization, first, we perform a pre-evaluation technique, discovering that the best case was with 4 bits of pre-evaluation. In this way, we are able to disable most of the input register and just work with a subpart of the component, reducing the switching activity. Then, since the total 2/3 of the total power are still consumed by the register, we decide to adding also clock gating technique. And in this way, the overall performance are really improved. As we can see from the graph on the right, the dark blue bar are about the optimized version. Instead, the light blue are about the basic version. In particular, the power is more than halved in the optimized version. We have also some improvement about delay and area, and a final comment can be done about the power delay area product, which is around 1/3 for the optimized version with respect to the basic one. Now let's continue my colleague Ilaria Bosco that will talk about the integer divider. Thank you.
Okay, the next considered operator is the integer divider, and among the plenty of architecture proposed by the literature, the non-restoring divider is selected. This method is quite similar to the pen and pencil approach, so starting from the most significant bit of the dividend, we subtract or add the divisor depending on the signs of the dividend and divisor themselves, and from the evaluated partial remainder, one single bit of the quotient is computed. Then the same operation are repeated several times in order to evaluate all the bits of the quotient. In order to try to optimize this complex operator, several techniques have been applied. First of all, trying different architectures for the main built-in block, the adder, so ripple carry adder, carry select adder, and elm adder are considered, and the last one is considered as the best choice, while clock gating and prevaluation have been applied in order to try to reduce the power consumption. But for sure, the most fundamental technique was pipelining, because of the long critical path that along all the divider, because the operation of each adder depends on the result of the previous one. For this reason, I don't know. For this reason, several attempts have been made in terms of number of pipe levels to try to reduce the critical delay. Of course, increasing the number of pipe levels will decrease the delay, but increasing the power, the area, and the execution time. In the end, the solution with the 12 pipe levels was selected in order to make the critical delay similar to the one of the other operators, but still trying to keep under control the other matrix. As natural consequence of the integer divider, the floating point one was implemented, and as in all the floating point operator, we have to deal not only with the significance, but also the exponents that in this case are subtracted, the valuation of the sign, and the handling of the spatial input. But putting attention on the algorithm used to implement the significant dividers, SRT and Goldschmidt algorithms have been considered. Looking at the main equation of these two algorithms, SRT is still based on adders, and in particular one adder per iteration, and considering a radix 4 approach, 26 iterations are necessary. In this case, two versions have been developed, one considering carry-save adders and the other instead with non-redundant adders. While Gauge-Schmidt divider need for per iteration one adder and two multipliers, but in this case the number of iterations depends on the wanted precision of the final results. In our case, it is decided to implement 5 iterations. In this case, looking at the results, the Gauge-Schmidt solution is considered not feasible because of the too large area and power consumption still to have approximated results. While comparing the two solutions that developed the SRT algorithm, the redundant solution, so the ones based on carry-save adder, has better results in terms of delay and power, but still approximated result. And because of the mean error is low, but the standard deviation is not, at the end is decided to choose as final solution the one based on non-redundant adder. And as always, clock gating was implemented to try to reduce the power consumption. In the end, some summary data were collected for the final architecture of the integer ALO and the FPU. And as expected, the divider is the most impacting operator in terms of area and power consumption, followed by the multiplier, and then the multiply and accumulate. And the divider is also the operator that determines the critical delay of the overall structure. And then similar results are obtained also for the floating point unit with always the divider that is a sort of bottleneck of our architecture. And with this consideration, we can concluded the first part of the workshop dedicated to the design of our architectures.
Hi, everyone. The aim of the second part of the workshop is the mapping of the designed architectures in advanced FinFET technology. The advantages of using triple gate structure FinFETs is an improved electrostatic control of the channel and a reduction in short channel effect that become dominant by scale devices. We have used the BSIM model with an SOI substrate, a channel length of 14 nanometers, 7 nanometers fin thickness, 30 nanometer fin height, and so on. Firstly, we have analyzed the electrical parameters of our FinFETs by comparing them with a benchmark made of 45 nanometers MOSFET. We can see that the ratio I-on over I-off is significantly increased from 1.2 times E to 4 to 5.6 times E to 7, so of a factor greater than 10. The threshold voltage is 350 millivolt, and more important is the reduction in the subthreshold slope that is now 66 millivolt per decade, near to the minimum possible value of 59 millivolt per decade. By analyzing the dependence on the fin thickness of this parameter, we can see that the I-off current increased exponentially, and this is due to a reduction in the threshold voltage and an increase in the subthreshold slope. This highlights the importance in reducing short channel effect of controlling the fin thickness. Then we have characterized an inverter. We can see from the first three parameters that we have significant large noise margins near to the maximum possible value of 0.5 volt. And also the slope, the maximum slope, is increased of a factor equal to 3 from MOSFET to FinFET. but more significant is the reduction in the propagation delay f4 of an inverter loaded with 4 identical inverters. By varying the fin thickness, it can be seen that the maximum slope significantly decrease, and this means less regenerative power, and also noise margin decrease. That means a less ideal static characteristic. Rather than we have an increase in the propagation delay and an exponential increase in the total power, maybe probably due to the static power contribution. Then we have described several gates by using FinFET, and we have done firstly a timing characterization on them. We know that the propagation delay of a gate can be expressed as the sum of the intrinsic delay due to parasitic capacitance plus a factor times the load capacitance. Since these parameters depend on many factors, we have done some assumption. Firstly, was chosen an input configuration for worst case delay, where imposed the rising and falling time of input wave equal to 5 picoseconds, and then the mean value of high to low and low to high transitions were extracted. The results are shown there, where can be seen a significant reduction in the intrinsic delay of a factor equal to 3, a slightly increase in the K-load, but is also important to notice that the input capacitance of our logic gates is significantly reduced of a factor almost equal to 6.5. And let the control to my colleague.
Thank you, Michelangelo. Now we can proceed with the last part of our presentation. The next step was, after characterizing the gates in terms of performance, was to characterize them in terms of power consumption. So power is made of a dynamic part, which is dependent on the switching activity of the device, and a static part, which is dependent on the leakages. We have computed the total power dissipated by each cell by integrating the total current that was drawn from the power supply over a period of 1 nanosecond, and then by multiplying that by VDD. Then DC analysis was used to estimate the static power for each gate. And since the conditions in terms of load and of supply voltage were such that the switching power was equal to 1 microwatt, we were also able to isolate the short circuit power. And as we can see from the pie chart below, we have that the switching power is the largest contribution in terms of power consumption, followed by the short circuit power, which is about 1/5 of the total power consumption, while the static power is practically negligible. Okay, then we have used the characterized cells in order to design a few arithmetic blocks by manually designing the schematics. And this was done with a hierarchical organization of the schematics in order to test smaller units and to build up the device. We used a Verilog module to describe the input generators, and we used also scripts in order to automate the simulations. Out of this, we were able to have 2 figures of merit for our devices, both the delays in terms of critical path and the power, which was evaluated integrating the current drawn by the device in a scenario where we had a sequence of 100 random stimuli, input stimuli. For example, this is the 8-bit Almader that we have designed by using the cells in the FinFET library, but also those in the standard CMOS libraries. And from this, we can observe how by changing the technology, we were able to reduce both the power consumption of the device by a significant amount, but also the delay of the device. And we can also mention that there is a reduction of the current peak, which leads to a more reliable device. Then, as a last thing, we have tried to play with the parameters of the FinFET library, and we have changed the working functions in order to decrease or increase the threshold voltage of the FinFETs. This allowed us to build a high performance and a low operating power version of the same devices. But we can see from the bar plot on the left that the default values for the working function gave us the best power delay product. So they were the best values in order to obtain this compromise that we wanted to achieve. Then we took the 3 scenarios in the HP case. So we took 3 scenarios with lower threshold voltage than the default threshold voltage. And then for each of them, we have tried to scale the VDD in order to obtain the same delay as in the default case. But also in this case, we see that with the default parameter set, we get the optimal power delay result. So this finishes our presentation. Thank you for listening. And if you have any questions, do not hesitate.
Okay, thank you. If there are questions, you can type your intention in the chat and we will give you the word. And in the meanwhile, I have a question, so probably I can start. The question is twofold. Did you find more challenging the digital design optimization, and I mean from the standpoint of the architecture and algorithm design, or is a technological implementation oriented to your specific optimization goal? And this is the first question. The second is, at the end of your work, do you think FinFETs are intrinsically suitable for your optimization goal, or the number of compromises you accepted is somehow a symptom that technological constraints are a limit, a real limit in this direction?
Maybe I can start to answer to the second question. So I think that we have found that FinFET are perfect for our aims because they allow us to have almost the same ion current, but by reducing the I of current. This means that we have we don't have an improvement in performance, but we can, by reducing the area also, we can obtain better performance in terms of power. So I think that FinFET can allow us to reach the target of best low mix implementation of the product of power and delay. And for about the first question, I can say that I don't know if it was more challenging, but maybe I found the first part more interesting because I found more interesting architectural design to respect with technological design. So about interests, maybe the better one for me was the first part. About challenging, I don't know. I don't really know. Almost we have done the same amount of work for the 2 parts, maybe more for the first part, but I can say that one of them is more challenging to respect with the other.
I can say also my personal opinion about this last. Also, in my case, for sure, the design, the digital design optimization from an architectural point of view was more interested. Also because from a technological point of view, it's not so easy to really trying to change the parameters of the model and also get some interesting result. Of course, our model very complex and already optimized in terms of parameters. It's really complex to get interesting results. While for sure, also from thanks to my background that is more architectural, instead in the architecture I could appreciate more the results and yes, just not try, but think a strategy before starting, and so when I start, I can a bit imagine if it could make sense for the optimization or not.
Okay, thank you. There is a last question that is not coming from the chat, neither from the room here in presence. And the question is, did you use bulk FinFET or SOI1 FinFET? Probably you said, but...
Yeah, SOI FinFET. Yeah.
Okay, thank you. If there are no questions, we can proceed with the presentation. So we can proceed with the third group. The target was high speed, so maximum performance. I ask to the members of the third group to switch on their cameras and to proceed with the presentation. Okay. Perfect.
Good afternoon to everyone. I think we are at the end of the presentation. Little mistakes. Okay. I'm Alessandra, and I'm a member of the high-speed group. During the entire project, our goal was to design, optimize, and characterize the device we work with in terms of speed, trying to achieve the fastest performance. The entire project was divided into two parts, an architectural part whose goal was the design of an arithmetic logic unit and of a floating point unit, and a technological part whose goal was the implementation of the arithmetic and the logic block design, exploiting new advanced technology. In our case, to achieve high performance and high speed, we exploit GAFET technology. In this brief presentation, we will explain our result. Regarding the first part, initially, we have defined with the other group a common design rule to achieve a uniformity of the code and of the interface of the different components. Accordingly to these rules, we have modified the inherited components of the last year project and designed the new ones. Secondly, we focus on optimizing in terms of performance the different components. These are all the components that we have inherited from the last year innovative system workshop, while on the right column, you can see the new component that has been implemented this year. The preliminary work was focused on literature researches about possible architecture for the different operators chosen. After the description phase in the HDL, we have simulated the block with model sim and check its current functioning, exploiting some Python scripts. Once the basic implementation works, we proceed with the different optimization and then with the synthesis and the place and route phase. We mainly apply two kinds of optimization, manual and automatic one. Manually, we first try alternative architectures and rearranging the critical path of the design selected. Then, in order to speed up as much as possible the frequency, we apply pipelining and pipelining interleaving to cut the longest combinational path. Automatically, we instead exploit a synopsis tool through different specific commands, like shown in these slides. For the verification process of each component, we create a Python script for generating the input vectors, and this, together with the VHDL files, the test bench files, and the simulation script, was used to run the model sim simulation. The output vector produced has been checked, comparing it with a reference output file. The results are then saved in a log file, which report eventual error. Once all the components have been designed and tested individually, YALO and FPU were designed as two standalone components. We create again a Python test in order to simulate a control unit that is able to handle them. The schematic here show represent how the Python script has been organized to handle all the different components of these two units. For our assumption, they execute one operation at a time in order to avoid that results from different operators are simultaneously ready at the output. And only in the case a new instruction involves the same operator, the pipeline structure is actually exploited. Now I leave the word to my colleague Francesco, who will explain in a detailed way the one of the components that we have implemented.
Thank you, Alessandra. Hello, everyone. I'm Francesco. The developed component we choose to show you is the floating point divider. It is a single precision floating point divider based on an iterative algorithm that needs 5 clock cycles to compute the result. If desired, the algorithm can be quite easily scaled to work with double precision floating point numbers on 64 bits. According to the other groups and to the inherited components, we use truncation as rounding. And in addition, we developed 4 different versions with different delay power area trade-offs. Since our goal was speed, we applied different optimization techniques to improve our component in the direction of performance. The diagram shown here is the heart of the divider that is in charge of computing the mantissa of the quotient and remainder. We have not enough time to go into the detail now, but we want only to highlight that it consists of 3 stages in cascade that make the critical path quite long. Therefore, in one of the 4 developed versions, we decided to pipeline the structure. As known, pipelining shortens the critical path, but it worsens the area, the latency, and in most of cases, the power consumption. Another bottleneck reducing the throughput is the iterative nature of the algorithm. Thus, a feedback path is present, make the architecture busy for 4 clock cycles. For this reason, new data have to wait until the previous operation is over, with a reduction of the throughput by a factor 4 with respect to the optimal one. The solution is represented by a replication of the iterative stage as a sort of unrolling in such a way that the feedback path disappears and new data can come in at each clock edge. The throughput is 4 times higher, the latency and the critical path do not change, but the area and the power consumption increase significantly. Here, the delay and throughput results before and after the application of pipelining and pipe interleaving are shown. The red and the blue bars represent the results after the synthesis, respectively with and without additional optimizations made by a Synopsys synthesizer through the command written below. As you can see, the delay decreases by 30% thanks to the pipe stages, even though the fine-grained pipelining could have given even better results, while the throughput increases by 6 times. However, the latency passes from 5 clock cycles to 13 clock cycles due to pipe stages. About the power and area, they basically are 3 times higher as expected. As usual, no free lunch, and the versions with a better trade-off and intermediate performance could be considered. Accordingly to the specification arranged with the other groups, each component must have an input and an output register. Therefore, the minimum latency required is always 2 clock cycles. The maximum latency, indeed, varies according to the considered unit. For the integer ALU, the implementation of each operator with the most suitable delay was chosen to obtain the best possible performance. Synthesis enhancement commands has been then exploited, as shown before for the floating point divider. The same applies to the floating point unit. Lastly, we would like to highlight some considerations on energy that is spent by each component to perform the operation. For the ALU, the maximum energy is associated to the integer divider, while for the floating point unit is associated to the floating point inverse square root. In both cases, the 2 operators have the highest latency and the highest power consumption. Finally, we have proceed with the place and route phase for both the unit. In order to avoid all times violations, the clock period has been increased both for the ALU and for the FPU. Final results are shown here. About the performance, that was our target, we get a minimum clock period of 1.66 nanoseconds for the IALU and 2.8 nanoseconds for the FPU. You can also notice as the power has increased significantly after the place and route due to parasitics. I will now let the word to my colleague Sara, who will talk about the second part of the workshop, about the technological level.
Thank you, Francesco. As my colleague just announced it, me and my colleague Pier Francesco hereafter will explain the route we took to arrive at the simulation of the previously ALU and FPU blocks we have just described, this time with a GAFET library, not the standard 45 nanometer CMOS one. As here outlined, As outlined in this slide, we mainly followed 6 steps. We exploited Virtuoso for both the GAFET characterization and the logic gate realization. In particular, we evaluated the GAFET main figure of merits, highlighting the advantages and the disadvantages with respect to standard technology. Then we moved to the cell characterization through Liberate in order to get to the definition of a GAFET library. Finally, we synthesized the ALU and FPU blocks through Synopsys, of course exploiting the aforementioned new cell library, in order to conclude with QuestaSim for the block simulation. But first of all, let's investigate why GAFET technology. As concerns this project, GAFET has proved to be the technology that best met our need in terms of high speed and performance. But if instead we want to move on a global level, at the moment, the latest IRDS guide published in November 2021 predicted a transition to GAFET devices to start, potentially for 3D hybrid memory and logic applications. Moreover, the market too is moving towards this direction. Samsung has already announced the introduction of nanosheet GAFET in 2022-2023 for the realization of the 3 nanometer node devices, whereas TSMC will migrate from FinFET technology to GAFET 1 for the practical implementation of the 2 nanometer node transistor. But why did they introduce nanosheet GAFET? They decide to use nanosheet GAFET to face the different problems, especially in terms of layout, cost, and performance, encountered with the scaling of the FinFET technology beyond the 7 nanometer technological node. In fact, GAFET have been recognized as excellent candidates due to superior channel electrostatic control and great drive current. Furthermore, GAFET devices help in supply voltage reduction, enabling a consequent power scaling. In this slide, indeed, I will briefly present you which is the GAFET structure and which are the most important technological parameters our BSIM CMG model was based on. The model was implemented in Verilog A, and in particular, the parameters we show here are also the same that the IRDS proposed in 2021. I would like to mainly focus your attention on the fact that we can increase the control current thanks to by changing and by increasing the number of nanosheets and the width of each nanosheet. The value here reported, however, have been proven to be the optimal ones in terms of trade-off between speed and power consumption. Finally, both N and P GAFET characterization has been done in terms of 5 figures of merit: ion current, I of current, subthreshold slope, and drain-induced barrier lowering, and the ratio between ion over I off. As we can notice, the ratio between ion and I off is 10 to the power of 6, and this is a very promising result if we consider that this figure of merit allows us to evaluate how good a technology is, and if we consider that the minimum value of this figure of merit is 10 to the power of 4. Now I'll leave Pierfrancesco to continue to talk about the logic gate characterization.
Thank you, Sara. Once technological parameters are defined, as explained before by my colleague Sara, it's possible to proceed with the logic gate design. The main goal of design is to get cells as symmetric as possible. For this purpose, the transistor in pull-up and pull-down network were designed in order to be crossed by approximately the same amount of current in the worst-case scenario. A limited set of cells were designed in cadence Virtuoso in order to obtain a cell library that allows Synopsys to synthesize components. Once the Virtuoso library is completed, all the cells can be characterized. For this purpose, Cadence Liberate may be exploited, and this tool makes the logic gates characterizations, both from timing and power point of view, simpler and faster. It requires basically operating conditions like supply voltage and environmental temperature, N-type and P-type GAFET Verilog A models, netlist describing the logic gate, and template of tables in Liberty file, as the one reported in this slide. Logic gates were characterized one at a time, then a Python script was exploited to put together all the characterization results in just one Liberty file. At this point, all the components designed in the first part of this workshop can be synthesized, mapping each netlist to our cell library. On one hand, the library compiler can be exploited to generate a library readable by the same compiler, so that a synthesized netlist can be generated. And on the other hand, Liberate can be exploited again to generate a RTL description of our library. In order to check the behavior of the synthesized netlist, a simulation can be performed on Model Sim. At this aim, both the netlist RTL description and cell library are required. Once again, a Python script was exploited, but this time a reference model was implemented in order to verify the correctness of results obtained from the simulation. The comparison between results generates a log file, and the absence of errors in the latter proves as the designed cell library works properly and can be used for the synthesis process. That's all for the high-speed group. Thank you for your attention, and don't hesitate if you have some questions.
Okay, so thank you very much. If there are questions, again, you can type your intention to ask a question in the chat. In the meanwhile, I know that there is a question here in presence.
Yes. So what about the sensitivity of the performances of the cells that you simulated and characterized with respect to the channel or extensions doping of the transistors, if you investigate it? Is it clear?
Can you repeat the question? Sorry.
Yeah, I was wondering what about the sensitivity of the performances of the cells that you simulated with respect to the channel or extension doping of the transistor, if you investigated it.
Okay. Yeah. Okay. I can answer to this question. We mainly focused as regards the doping concentration and as regards also the doping concentration of the channel. We mainly focused on the characterization of the single transistor, both N and P GAFET, because we had some problems in terms of tool convergence when simulating some cells. When the doping concentration was the default one, which was higher with respect to the doping concentration that then we chose for the simulation of the other cells. And in fact, what we did during our route was to decrease both the doping concentrations of the source and drain regions, but also of the body, in order to maintain constant the ratio between the two. And of course, this led us to obtain worsened result with respect to what we expected. Because since the doping concentration has been decreased, the delay has been increased, and so we had troubles as concerned our goal of high speed and performance. However, we had a good news, because even if we decreased the doping concentration, we succeeded in increasing the ion over IOF ratio. And in fact, with the default doping concentration, we had an ion over IF ratio of 10 to the power of 4, and so it was at the threshold, it was at the limit with respect to an acceptable value of this figure of merit. And instead, when we decrease the topping concentration, it has increased of 2 orders of magnitude, because especially the IF current decreased a lot, and so it became of the order of 3 ampere.
Okay, thank you. Very interesting.
Thank you.
Okay, I have another question that's probably connected to the one you have already answered now. Few companies around the world has already announced the imminent release of nanosheet gate-all-around FET-based integrated circuits. So on the basis of your work and on the basis of your experience, what do you think might be the main challenge in performing design with such technological nodes? What I mean is power density constraints. We will talk again of dark silicon, alternatively standard cell performance to ensure correct system behavior or process reliability. What could be the most critical part of design?
Yeah, the main problem, I think, as concerns GAFET, is the fabrication step, and also because of course the fabrication process is mainly similar to the FinFET one, but the main problem is that it is of course made more complicated because of the structure of the GAFET itself, because it has we need to realize the different nanosheets within the same fin. But also the problems are related to parasitics, because since we can increase, it is true that we can increase the control current, the drive current, by modifying the width of the nanosheet, but at the same time, if we increase such parameters, we also automatically increase the value of the parasitics, and so this can be a problem, especially in terms of both in terms of speed, because the higher is the amount of parasitics, the higher is the time we need to observe a response of the different cells. But of course, the higher is the amount of the parasitics, the higher is the power consumption when switching on and off the device. And so it is always a matter of finding a trade-off between the different figures of merit. But for sure, I think that this is the most promising technology we have to focus on in terms of digital integrated circuits.
I can add something. I heard that from the point of view of the analog design, it's more difficult to deal with these new technologies, such as FinFETs and moreover GAFET, because the layout rules you have are really strict. So it's really difficult to develop a layout without have a lot of iterations to check the design rules. So another problem could be the compliance with the design rules with the analog layout. That can be a problem, and so it's not so simple to use this technology in that field. So this problem is present with FinFET, but with GAFET is even more complex.
Okay, thank you very much. We still have another question here.
Yes, I have a question regarding the architectural phase. You mentioned that you applied some automatic optimization by using Synopsys design compiler, but did you investigate more in depth what kind of optimizations are applied to your design?
Yes, I can answer this question. So I can find the slide when I have the comment that this one. So these are the comments we gave to Synopsys. So the first flag, exact map, is a flag to tell to the synthesizer to synthesize the sequential elements without changing too much. So it's basically a way to have a more reliable, so a more reliable design. So if you do not have the exact map flag, you could have a design that is different with respect to what you wrote in the VHDL for some reasons. So we use that command to have a predictable result from the point of view of the sequential elements. The second command, map effort high, is about the effort to find the good mapping for the gates. In our case, for the performance. So in this way, the synthesizer spends more time on the mapping phase, and then the result you have is better. The boundary optimization and the ungroup all are related because they are commands that are used to unflatten all the hierarchy. So you have a component, you have different blocks. I don't know, you have an adder, a multiplexer, and so on that are nested in an hierarchy. With the ungroup all, these blocks are disassembled, we can say, in such a way that optimizations between the boundaries of the different components can be achieved. So the different blocks are not treated not treated as a single block as distinct blocks, but are treated as a unique logic gates C, you can say. So with ungroup all and boundary optimization, the synthesizer can optimize in a better way your design with respect to the case in which you do not use this command. So this is what we learned about this.
Thank you.
Thank you, Francesco.
Thank you. Thank you very much. I don't see questions in the chat, so probably we can proceed, also because time for questions is a bit out. At this point, before concluding this event, I would like to leave the stage to Professor Maria Grazia Graziano, who is now connected with us. She also followed the workshop together with Professor Gianluca Piccinini and Maurizio Zapponi, and together also with us. So probably now, Professor Graziano.
Yes.
Okay.
Hello. I don't know if I also can connect.
Yes, we can hear you. Yes.
Okay. Okay. I will not join with the video. Sorry, I'm in a room with other students, so it's better if I just speak. I just wanted to congratulate with all of you for the results and for the level of competence that I have heard that you have reached at the end of this work, and this gives a level of thankfulness for all what you have done. So I'm really feeling thankful for all of you, and not only for the students, of course, but also for the PhD students that attended and helped to reach the result that we have seen, that are really, really impressive. And so again, I want to congratulate and give you a big, big thank. I now leave the word to you, that you organized everything, and I hope that you are, let's say, that you are feeling happy for what you have done.
Okay, thank you, Professor Graziano. I think we can go towards the conclusion of this event. But before concluding, I would like to ask to all the people, the students, to please switch on the webcam, and also to the colleagues who are available and able to switch on the webcam. I also switch on my webcam. Okay, everyone is here, more or less. Okay, so before concluding, I just would like to say a few things and to ask a last question for this workshop, because all of us for sure understood that the workshop is not only a technical course, but there is something more about skills. And I'm especially talking about soft skills. I know that behind the workshop, there is also a lot of communication and a lot of team working inside the group. So internal team working in all of your group, but also in terms of intercommunication among different groups. So I would like to add a last question to you, to all of you, and ask, how did you manage the communication and the cooperation inside your group? And what is the most relevant skill that you acquired during this experience? So if you give us a brief comment about basically this workshop. Of course, all of you can answer. Feel free to start and to continue this answer.
Maybe I can say something, since
yes,
I didn't tell nothing because of my connection. Well, I will say that for the soft skills, we learn so many things. First of all, from my point of view, mainly the organization of the work was increased. We were able to split our responsibility in a better way, since all PhD gives us some advices in order to do that. So split the responsibilities within the group. And basically, we identify 4 different roles. So each of us has a different role inside the group, and we were able to understand which were our limits and which things were what we have to do inside the group. One of them, we can say that was responsible also for the communication within in the intergroup communication. So with our group, the low speed one, with the mix and the high speed. So I found this kind of organization very useful, and also to understand which kind of responsibility has every people in a group. I don't know if also my colleagues have some words to say about that.
I don't have anything to say about this, because I think you explained it very well. I think I was we were all agreeing together, we of the low power group, is that we for sure learned the ability of adapting to any kind of difficulty that comes against us without us expecting it. And of course, we unfortunately had it today, but it also happened several times during this project, which lasted a year. And also, I think this is a very useful skill that we all acquired.
Yes, I would add the fact that we actually grow because we were left free to do our choice and evaluation, and we need to manage the time we have alone, which is completely different with respect to the laboratories we were used to do in the different courses of Politecnico. And we have for surely learned that also failure can become a moment of growth for us, because we surely encounter, as my colleague said, a lot of problems, and with the help of the other group, with the help of the PhD students that follow us, we were able to solve them and learn from them. And in addition to that, we have also learned how to become more professional in reports, in presentation, in explaining our work to somebody else, which is something really important, in particular for the future. So I will thank you, not only my colleagues, but also the PhD students that follow us, because they help us in understanding all these things that are not something that we learn in common lecture, let's say. So thank you for that.
And if I can add a word for the mixed group, I can say that the workshop has been an opportunity also to enrich our communication skills, both for communicating inside the group and among the groups, but also because we had to present this final work, and we had to synthesize a work that was carried out during a year long. So synthesizing and presenting things in such a way that were clear also to other people was not easy, and was the first time we actually did that for something so big. And from a more technical point of view, we actually learned a lot how to dive deep into a very big project where there is no predefined solution, no trivial solution, and where we have to carve our own solution, basically, by studying the literature and by coming up with ideas. So it was a very good opportunity for both kind of skills, either hard skills and soft skills.
And if I can add something, also the ability to start working on something that was already started by someone else, in this case by our colleagues of the last year, and not by starting from zero, as we are in most of the cases we are used to start from zero for our laboratories, for our other projects. And in this case, it was a little bit different from this point of view.
Okay. Any other comment? Okay, so thank you very much for sharing these answers. Very interesting. Thank you a lot for this. And I would like to conclude the final presentation by saying a big thank to all of you, because I think you did an incredible work, and for sure it's valuable. So a very, very good work. It was a very good workshop, in my opinion, and I would like to say a big thank also to the people who is behind this workshop, that are for sure Professor Maurizio Zamboni, Professor Gianluca Piccini, and Professor Maria Grazia Graziano. And of course, I would like also to say a big thank to my valuable colleagues who are here, Andrea Coluccio, Fabrizio Mo, Chiara Fispano, and also Fabrizio Ottato. Last but not least, I'd also like to say a big thank to the IEEE student branch of Politecnico di Torino, who helped us in the organization of this final presentation. So thank you to everybody, and thank you also to the people who came to this final presentation and who listened to our presentations. Thank you, and see you soon.